the principles of applied rock mechanics, which we have done now, are normally considered to determine the following to achieve stability for underground structures. So we are looking at the overall mine layout, the relative location, and interactions of the entries and the pillars, sections, or panels of the mine. That is what we are looking out for in terms of rock mechanics. Then the shape, size, and numbers of the entries. These are analysis we do can help us maintain stability in all of these. Then optimum support system for structural stability and control the failures that may arise. That is what applied rock mechanics is about. So pillar loading. So pillars are that portions of materials left in place to support the opening. They may or may not be extracted after mining. So if we have pillars and they are rich in ore, we may choose to or may not. So who can help us? At what point may we and at what point may we not? Who can help us? What instances will we consider to either extract our pillars or to leave them even when we are no longer mining? Any help? Hello?
Yeah, Doc, I think that if we suspect if we mine the pillars, it will kind of create some voids up. So I mean, like we wouldn't have to take it off, not to create those voids.
Okay. All right. So then who again? Any other contributions?
When we can mine out the place when we want to practice the refilling method.
Okay. If we want to practice refilling, so we can go for our pillars and then bring in foreign materials and then use that to enhance the stability. Okay. So they are more or less square or rectangular in shape for supporting and maintaining rooms and entries. So however, diamond-shaped pillars are also frequently employed so that mining machines can negotiate bends or turns. So what we are saying is that although we have the pillars and we are saying that you should try the square ones because they will facilitate your job as the engineer. But then sometimes these pillars, when they are rectangular or squares, because of the curves, the sharp curves, have also issues with negotiation, how your trucks or loaders negotiate the various curves within, and you have a lot of bumps and blind spots. So some people try the diamond-shaped pillars where they look more or less like hexagons and these things we've been talking about. So they're more or less like rounded. But in that case, if you have a way of computing for those sizes in the diamond shape to facilitate your calculation, so that you can tell your manager that these pillars I have installed, if we mine at this area, we are expecting an 80% extraction rate. Fine, go ahead with your diamond shape. Otherwise, you should go for techniques that you yourself can facilitate your work and help others to understand you better. Barrier pillars are located at both sides of each entry and between sections to separate mine out sections from virgin sections. So there are two theories in all these calculations we've been talking about for evaluation of whether the expected load history will crash the pillars. So if we are talking about whether our pillars will crash or not, people have come up with two things. We call the ultimate strength theory and the mechanism theory. So the ultimate strength theory says that strength theory contends that pillar will fail as soon as an applied load reaches its optimum strength of the pillar. So once I have a pillar, the pillar has how much load it can bear. So as soon as any load exceeds the strength of the pillar, there is collapse. That is what this theory is saying. And it presumes that the load bearing capacity of the pillars just reduces to zero at that point in time. The moment you exceed me, I become zero and I can no longer provide support. That is the ultimate strength theory. And then the progressive one also says that this emphasizes the existence of defects and non-uniform stress distribution in the pillars. So this particular theory is considering the various non-uniform distribution. For example, you have pillars that are not evenly distributed. Then it means your stress will also not be uniformly distributed in all the pillars. You might have certain pillars bearing more stress than the other. So this progressive failure or mechanism theory watches out for the non-uniformity of the stress distribution. And it then further adds that failure initiates at the most critical points and propagates gradually to ultimate failure. So as soon as it finds the weakest spots, immediately failure initiates from there, and before you know it, the grand failure occurs. And as soon as this grand failure occurs, then it means we are validating the ultimate strength theory. It means that your load has exceeded the strength of the formation. So the data required in designing pillars, regardless of theories, are: one, the expected load history, including the pre-mining pillar loading and mining induced pressure. These are what we require. The stress distribution within the pillars are required. The pillar strength is to be known. The interaction between the roof, pillar, and the floor must be determined. These are data we gather. So maybe you are looking for a topic. You can investigate this as a review for your project work or your thesis you're about to work if you work in an underground mine. Then when the tributary area method of stress analysis is used in the designing in a flat line or stratified ore body, 5 parameters are involved in the design analysis. So the field, so here it is talking about if you want to use the tributary area method, we consider this in a flat line deposit. The field stress component acting perpendicular to the plane of the ore body is determined by geomechanical environment. So the 4 variables established are working or the pillar height. You should know that. The room, slope, span. So if you have the room or the stope, sorry, this is stope. The stope span, which is the width, okay? Then we have the width of the pillar. These are just more or less like a revision of the various parameters we have considered in the tributary area analysis. Then the factor of safety against failure. So then the final section, and then maybe we will end the lesson. So the selection of appropriate factor of safety here against pillar failure is based upon engineering experience. So if you want to select an appropriate factor of safety, it is based on your experience that you decide whether if I have 1 point so and so or whatever. But then combine empirical formula for determination of factor of safety. A lot of people have come up with studies determining factor of safety about pillars. And then finally, the one that most people love to go by is this man, Solomon's. he came up with this Hundius formula saying that the pillar strength is equal to 7.18, the height from the top of the surface to the point you are putting your pillar, to the power minus 0.66 times the width of your pillar to the power 0.46. And he is saying that no matter the kind of mining arrangement you are doing for your pillars, your factor of safety for pillars, if you want to be on the safer side, minimum at all should always be 1.3, up to a maximum of 1.9. But then, if you are in between, it's ideal. So if you want more factor of safety, it means that your weight, so he's considering the weight as a component here. So the weight of the pillar is a major component in determining the pillar strength. So if your weight is wider, you are likely to get a very good factor of safety or pillar strength. But let's watch. So a 2.5 meters thick horizontal ore body is located at a depth of, so who can tell us this based on our calculations we've done so far? The 80, who can tell me what value it is representing? What is the 80 standing for?
Dog, the length.
Is what?
The length.
What length? Define it appropriately. Is it length? Length of what?
Doc, I think the 80 is the height of the pillar.
A 2.5 meters thick horizontal ore body is located at a depth of.
Doc, that's our age. That's the height from the ground.
That is our age. Or in other jurisdiction, you say the Z from the top to where the ore body is. That is. Then with the rock cover having a unit weight. So now from that surface to where the ore body is, that material there, which is the overburden material, the pillar, whatever pillar you are going to put in place is going to bear. The unit weight of that material is 25 kilonewtons per meter cube. An initial mining layout is based on 6-room span and 5 square pillars. Who can interpret this? Interpret this for us. If you understand these things, solving the question, you just bring your formula and put them in and pack. You're done.
It means the pillars are designed to be square, and then they are going to be 5 meter by 5 meter. That's the A side, and the B side will all be 5 meters. And then distance between one pillar to the other is 6 meters.
Exactly. So if we are going to have this AB, so the length and breadth of our pillars are going to be 5. But then to the next pillar, this distance between them is 6 meters. So calculate the factor of safety. If the factor of safety is not guaranteed, what modification to the design can you make assume full all body thickness of this is being mined out. So if you are mining the all body thickness of 2.5, you are assuming you are mining full all body thickness of 2.5. What can you do? So it means that in the modification you are going to make, you are not going to tamper with our all body. Let it be. We need it all. So that is what is there.